Another useful property of divisibility is that divisibility is transitive. So in other terms, if I have integers a, b, c, and a divides b, but also b divides c, then I'll know that a divides c. So for example, if I have integers a, b, c chosen as follows, a should divide b. So for example, I could pick 2 and 6 because a will divide b. And now I need to pick integers b and c that have the property that b divides c. So if I pick c to be, let's say, 18, this will work. Then according to this theorem, 2 divides 18. And you can try it out, you can verify for yourself. 2 times 9 is 18, 9 is an integer, so it seems like the theorem is actually true. So can you actually prove this theorem next? The proof here is pretty straightforward. We're gonna begin with a, b, c integers, and we want to assume that a divides b and b divides c. That was in the assumption of the statement in the theorem. Remember, our theorem says that a should divide b and b should divide c, and a, b, c are all integers. So now we would like to show that the first integer a divides the last integer c. That's what our comment is all about. Now since a divides b, then by definition of divisibility, there will exist an integer k, for example, where b is equal to a times k. But also b divides c. So by the same definition of divisibility, there has to be another integer, not exactly equal to k, maybe a different one, maybe t, where c is equal to b times t. So finally, if I write c and try to manipulate it, c will be equal to b times t because of the last assumption that we made on that line. But b itself is a times k, so we can do some direct substitution and replace ak in place of the b. But this means now that a times k times t is equal to c. But keep in mind, k and t are individually integers, so when you multiply them together, it will still be an integer at the end. Which means we have found the product of a times an integer that equals to the number c. So by definition of divisibility, a must divide c.